Okay, so we're going to talk a little bit about pendulums. We've done some work on the lab. Most of us are just about finished, so I'm going to start kind of going over what your results might have looked like. I'm going to start by looking at the relationship between length and period. Okay, so it's difficult. Hopefully you saw that as the length of the pendulum increased, so did the period. So like the longer it was, the slower it moved and the more time it took to complete an oscillation. But in order to really see the relationship here, it takes a lot of data points, and so I just want to kind of point out a couple things. I added a couple others, and I just want to show, like, if you were to try to draw like a straight best fit line here, you'd be going through the origin, or not through the origin, you'd be going through maybe like, I mean that's not a very good line, but somewhere between like in this region here as for your intercept. Okay, which means that if you had a pendulum with a length of 0, it would have a period of about almost a second, or yeah, close to a second. So does that make sense to you, that at 0 length the pendulum would still have a period? So what happens is that this relationship isn't linear, okay? And if you look carefully, you notice that it actually is going to kind of curve, okay? And so if we were going to do a fit for this, we'd actually find that it's a square root function. Okay, something on the form of y equals the square root of x. Okay, and if you were to continue working on that, for now we're just going to say this, that the period of a pendulum is proportional to the square root of the length of the pendulum. Okay, and that's kind of what we can gather from looking at this graph here, that it's curved, and I'm going to go ahead and make a jump for you and say that that's a square root function. And so what this would mean, and this is why it's really hard to see this in your data, it means that in order to see a lot of variation here, you have to increase the length more and more to see the variation. So it's really hard to get a square root function to look nice in your graph. But if you were to fit your data to a square root function, it would fit pretty well. And so that would be our relationship between period and length. Okay, so the next thing we checked was the mass, and I think a lot of us predicted the mass would be one of the things that made the biggest impact on the period of the pendulum. Or I guess we did angle next, but I'm going to look at mass next. And when we graphed it, you might have seen something like this, that it moved around a little bit, but generally there wasn't a lot of change. And if you even did like try to do a linear best fit line, you might see something, but it would just be a line with like a really small slope. And the reason why is because there's not really a relationship between the amount of mass and the period of a pendulum. Now, if you did get some variation here, it's because as the size of the mass increased, so did the length of the pendulum. So like if you're measuring, if one mass would measure to here for length, and then you have a bigger mass that's like this, it would slightly increase the length of your pendulum. And as we know, the longer the pendulum, the longer the period. So like when you put like the bigger masses on there, you might have noticed the period got longer by a little bit. And it's not by actually the amount of mass, it's because of the size of the mass you used. And so we have this relationship here that we came up with from before, that T is proportional to L. It looks like mass is not going to factor into this equation, because it looks like mass does not affect the period of the pendulum. So next we're going to take a look at the relationship between the angle of the pendulum and the period, and see what that effect was. Okay, so this is going to be kind of a similar thing. You might have noticed a little bit of variation, but overall it didn't seem like much. And even some of you came to me and said, well, is our data wrong because it went up and then went down, or something like that. And no, your data is not wrong. There's just going to be some natural variation. So if we were again to draw a line here, it looks like the period is not affected by the angle. Okay, and so again, going back to our equation, it turns out that so far the only thing that affects the period of a pendulum is its length. Okay, so it's somehow proportional to the square root of the length, but nothing else really. Okay, so and finally the last piece we looked at was the gravitational field strength, and we used the simulator to help us out. And hopefully what you started to see was something like this, that the smaller the strength of gravity was, the bigger or longer the period, the longer the time it was that it took to complete oscillation. So like when you're testing gravity on the moon, if you had a long pendulum, it might have taken you like 2 minutes to finish taking the data. And then as it increases, as the strength of gravity increases, the period decreases, and it kind of curves though. It doesn't look linear. It's curving and slowing down. So as the gravitational strengths get bigger and bigger, the impact it has on the period gets smaller and smaller. Okay, and so this relationship can be modeled using this function right here. So this is saying that the period, it looks like, this could be like a 1 over x thing. So maybe proportional to 1 over x. But in this case, it's not just 1 over x, or in this case 1 over g. It's actually 1 over the square root of g. Okay, it would be the function you need in order to fit this. Okay, so now we're going to take these two things and put them together. So the square root, t is, because period is proportional to the square root of the length, and it's proportional to the square root of 1 over g. Okay, and we can actually put these together since it's proportional to both. What that means is that t is proportional to the square root of L over g. Okay, and the thing that's really interesting about pendulums and any other kind of oscillatory motion is it's very cyclical. It's repeating. The process repeats itself over and over, and there's a lot of similarities between oscillations and circles. In fact, they're so similar that in order to make this into an equation for the period of a pendulum, we have to add some constant in front. So we have to figure out what we multiply all this by to make this true for every pendulum. And in this case, the number we multiply by is going to be 2 pi. So if we take the square root of the length of a pendulum divided by the strength of gravity and multiply by 2 pi, then we can actually predict the period of the pendulum. Okay? And so this right here is a tool that we use to make predictions about pendulums and use to maybe design the pendulum that we need in a certain scenario. Okay? So let's say that we were on, let's say that we're here on Earth and we want to make a pendulum. Let's say that we're making a clock. We want the pendulum to tick every second, which means we want it to go this way and then back this way. So we want to go this. So we want the time that it takes to go from here to here to be equal to 1 second. So 1 second, 1 second, 1 second, 1 second. Okay? If it's going that way for 1 second and then back that way for 1 second, remember a period is one full oscillation there and back. So the period in this case would be how many seconds? It would be 2 seconds, one for there, one for back. So if we wanted to make a clock using a pendulum, we would want our pendulum to have a period of 2 seconds. Okay? So t would be equal to 2 pi square root of L over g. We can now use this equation to figure out how long that pendulum should be. Okay? And so we'll put 2 seconds right here. 2 pi square root of L, and then we'll put 9.8 right here. Okay, so to solve this, we'll divide by 2 and divide by pi. Be careful when you put this in your calculator with order of operations. Okay, if you put in 2 divided by 2 pi, this is going to end up dividing by 2, then multiplying by pi, and it's going to give you 3.14, which you don't want. Instead, you need to divide by 2 pi. Okay, that will give you what you want, as will 2 divided by 2 divided by pi. So anyway, after you enter this into your calculator, you should get about 0.318 equals the square root of L over 9.8. Now you go ahead and square both sides. and get 0.101 equals L over 9.8. And to finish this off, you'd multiply both sides by 9.8. So that L would be equal to 0.99 meters. Okay? Okay, so what I'd like you to do now, let's say that we have a pendulum that we want to have a period of 2 seconds. Okay, go ahead and tell me how long we should make that pendulum. Alright, so we can divide by 2 pi, get that 0.477 equals square root of L over G. We'll square both sides and get 0.228 equals L over G, and then just multiply that 9.8 over and get that L is equal to 2.23 meters. So I just want to point something out. If we wanted to have a pendulum with a period of 2 seconds, then we would need it to be about a meter long. Okay? But if we want a pendulum with a period of 3 seconds, it would need to be about 2.23 meters long. That's a really big jump, because our brains are kind of wired to think proportionally, like linearly. This is not a linear relationship. So increasing by basically 50% does not increase that length by 50%. We would expect that, this would be closer to like 1.5, 1.7, 1.8, but it's actually, we need to more than double the length of our pendulum to increase its period by 1 second. Okay, and the longer and longer you want the period to be, the more and more length you're going to have to add, because it's that square root function, because it levels off really fast. Okay,